We've got Yuqi Huang here with us today, second year PhD student, correct? Yes. Yep, and so he'll be talking with us today about some urban heat island effects. So with that, I will hand it over to you.
Thank you. Right. Hello, everyone. I am Yuqi Huang, a second year PhD student working with Dr. Chenghao Wang on urban climate, land and atmospheric interaction, and multi-scale urban canopy modeling. And today, my topic is evaluation of a high-resolution operational numerical weather prediction product in capturing urban heat dynamics in a small city. So this is a project funded by NOAA with our collaborators from NOAA Air Resources Laboratory and Texas Tech University. So first, a little bit background. A recent report by United Nations shows that about 68% of the world's population is expected to residing in urban areas by the end of 2050. And in the US, about 96% of cities with populations larger than 20,000 falls in the range between 20 to 300,000. And those cities are defined as smaller sized cities. And as you may know, urban heat island by its bare form is relatively warmer of the city core than its surrounding rural areas. And this is caused by either the decreasing albedo or increasing heat capacity. And most obviously, the urban heat island effect is observed in those large cities. So the table 1 summarizes some observed UHIs in global cities, as you may see from New Mexico City, Beijing, and the average UHI. Okay, the average UHI intensity or UHII can reach up to 3 or 2.6 degrees Celsius. Whereas you may also notice that smaller sized cities such as Charlottesville, with a population of around 45,000, can also has the UHII reach to 2.8 degrees Celsius. And another great example is the 2021 US Pacific Northwest heat wave, as shown in this figure. So those red dots are stationary observed daily maximum temperature anomalies on 28th June 2021. As you may see, besides 3 big cities, Vancouver, Seattle, and Portland, there are many other red dotted across this region. So those are small sized cities. They also experience extremely high urban stress. So here we argue that small cities also matters in terms of urban heat stress. And then we focus on UHI in semi-arid area regions. And why? Because over 1/3 of the global population resides in semi-arid regions, and those areas account for about 40% of the global land. And also, the semi-arid regions features a positive feedback loop controlled by decreasing albedo. And this will lead to the region becomes more and more dry, and further intensifying the UHI of this region. And also, there are a lot of studies show that the UHI may be modified under different weather patterns. And the low 2 figures shows a good example. So, so the figure shows the shape of UHI in London, and the left one shows under calm condition or low wind conditions, the shape of the UHI is rounded within its center, while the left one shows under the westerly wind conditions with mean wind speed at 3 meters per second. You can see the shape of the UHI is kind of stretched towards the east. So we think without better quantification and representation of UHA, which is urban heat advection, we cannot better predict the urban heat island. And the model we will evaluate today is the high resolution rapid refresh, or HER model. HER model is a high resolution or 3 kilometer short term or hourly weather forecast covering the whole continent, and it has already been widely used in weather forecasting and the research field. And like many other numerical weather productions, the HER model also struggles to represent urban features. This is due to relatively finer or smaller scale features like intricate urban boundary layer dynamics, heterogeneous land cover, and anthropogenic heat emissions. And we also still don't understand if the HER model can better predict the urban heat advection under different weather conditions. So here, we want to investigate the spatial variability of urban heat and the urban heat advection in and around Lubbock, Texas, which is a smaller sized city located in semi-arid environment in the southwest US. And in order to do this, we break down into two tasks. The first is to evaluate the performance of the HER model against our observation data and try to analyze its relationship with the model grade characteristics. And second is to compare the modeled urban heat features with the measurement from the observation nights. And our final goal is to enhance the operational urban heat forecasting to support improved urban planning and risk management, and especially in those smaller sized cities. And next is the methodology. So first, there are about 28 sites deployed across the study area, and those sites within the center box are defined as the urban sites, and all the other sites surrounding the center box are defined as the rural sites. So we have 12 urban sites and 16 rural sites in total. And all the measurements are recorded at the 1 minute interval from July 1st to October 31st, 2023. And the right one shows the location of all the 28 sites, as you can see from those red dots. And then we identify the nearest sites, or nearest grid of those each sites as our HER grid, which are indicated by the blue dots. So we use all the blue dots and the red dots for our further comparison. And then move to data processing. So we have 23 micronet and 5 mesonet. So for the micronet, we obtained 2-meter air temperature, relative humidity, and dew point temperature. Those are all in local time. And for 5 mesonet, we have 2 additional variables, which are wind speed and wind direction. Those are in UTC. And for the identified 28 HER grids, we also have 5 variables in UTC. And note that all of our analysis are based on data from based on range from July 1st and October 31st, 2023. And we use the 20-hour focused output of HER data. So first, I'm going to show the spatial comparison between the model versus observation. So, so the upper panel shows the daytime comparison, and the lower panel shows a nighttime comparison. And from left to right are root mean square error, R square, and mean bias error. So these 6 are the 2-meter air temperature. So as you may see, the HER model tend to have a better performance at daytime air temperature, especially towards those urban sites. And during both day and night, HER can pretty well capture the temperature trend. And if you look at the mean bias error, during the day, the HER tend to slightly or overestimate air temperature. And during the night, the HER model tend to slightly underestimate air temperature, except for several sites. And we also show the dew point temperature compared to air temperature. The dew point temperature has a relative bad performance. And in terms of mean bias error, we can see both during daytime and nighttime that HER model showed an underestimation of dew point. And also, in order to better combine the effects of temperature and dew point temperature, we compare the relative humidity. So from the far right, we can see that during the day, there is a consistent underestimation of relative humidity for her model. And this is most obviously during the night, especially at those urban sites. And this is reasonable since her model tend to overpredict daytime air temperature and underestimate dew point temperature, which means her model gives us a relatively drier air. So that's reflected in the relative humidity. And as to wind component, since we only have those measurements at 5 sites, so here I only show 5 sites result. And indicated by the middle column, that the HER give us a moderate performance in terms of U wind component. And yeah, it gives us, the HER tend to overestimate U wind component, both during day and night. And as to the V wind component, as to V wind component, it has a better performance than U wind. And HER tends to overestimate V wind component during the night and slightly underestimate V wind during the day, as indicated by MBE. And next, we show, we have already shown the spatial comparison. Now is temporal comparison. So first, the upper one shows all the urban sites, and the lower panel shows all the rural sites. And from left to right are all time comparison, the daytime comparison, and nighttime comparison. And if you take a look at the upper right panel, we can see there is a slightly underestimation of her model, especially during the night at urban sites for air temperature. And as to the dew point temperature, from the middle column, we see a systematic underestimation of dew point, especially during the daytime. And this is more obvious towards the lower values. And the same pattern can also be observed from relative humidity. We see a systematic underestimation of relative humidity at both urban and rural sites during the day. So there really isn't so much urban-rural contrast reflected in the model. And as to wind speed, we can see a overall overestimation of the wind speed across both sites during the day, which is more obvious. This is also reasonable since the urban representation in land surface models adopted by the HER, they use a slab model, which eliminate all the building geometries. So the blocking effect cannot be affected, cannot be manifested in this model. So it tends to overpredict the wind speed. And then we also explore how the model performance can be related to the model characteristics. And here we choose urban fraction, greenness fraction, and albedo as the static variable used in HER to see how the dependency of the model performance on those variables. And to our surprise, we didn't see any clear relation between the albedo and the model performance for all those variables. And neither do we see a relation between all grid characteristics and model performance for relative humidity and dew point. But we do see a relation between greenness fraction and dew point performance. So if you take a look at the lower right, it seems that there is the model performance for dew point temperature increases with increasing greenness fraction. This makes sense because with increasing greenness fraction, there might be more vegetations, which means the model can capture the biophysical processes like evapotranspiration, and which will typically bring more moisture into the air. So that's why the performance of dew point temperature is like better. The underestimation tends to be eliminated. And then we specifically see the dependence of 2-meter air temperature performance on urban fraction and the greenness fraction. So the upper panel shows the performance with the urban fraction, and the lower one shows the performance with respect to greenness fraction. And if we see, as indicated by mean bias arrow, both mean bias arrow for air temperature has switched signs with increasing urban fraction and the greenness fraction. And we further break down into two. So first is the daytime 2-meter air temperature, and then we analysis nighttime 2-meter air temperature. So for daytime temperature, we can see that from the upper right, the model tends to over-predict or overestimate air temperature with increasing urban fraction. But we didn't see any patterns with respect to greenness fraction. And in terms of nighttime air temperature, we see a totally different pattern, because model tends to perform better with increasing urban fraction. And this is different from what we have seen right now. Before, yeah, this is daytime air temperature, and this one is nighttime temperature. So from our first task, we can draw several conclusions. But first, by the comparison of the observation and HER, we see the model tend to slightly underestimate nighttime, but overestimate daytime air temperature at urban sites, and HER tends to underestimate daytime dew point temperature at both sites. And we didn't see any pattern for wind speed. And by analyzing the dependence of HER model performance on grid characteristics, we see that HER shows a better performance with decreasing urban fraction for daytime temperature, but with increasing urban fraction for nighttime air temperature. And also, HER tends to underestimate dew point with decreasing greenness fraction, which might relate to the energy partitioning of the net radiation into sensible and latent heat. So this is the SLAM model and versus urban canyon model used in the model used in HER. So as I just mentioned, the HER model really used the one tile or slab model to represent the urban areas, which means during the day it cannot capture the shading effect. That might be the reason it gives us an overestimation of daytime air temperature. And during the night, typically in cities, there have the radiative trapping effect, which means the air temperature within the cities are really warmer than its rural. So without this trapping effect, the HER will give us an underestimation of nighttime air temperature. So yeah, this is related to the urban scheme used in different numerical weather prediction models. So we argue some better urban schemes in those numerical weather prediction models. And for our second task, which is a comparison of urban heat features by the model and measurement. So first, here is a heat map showing the measured nocturnal cooling rate. So the x-axis is our simulation period, and the y-axis shows all the 22 sites grouped by urban and rural. And the color bar shows the cooling rate. So the blue one shows the blue one shows nocturnal cooling, and the red one shows nocturnal warming. So this one is the measurements. We see 2 warming nights, which might be related to urban heat advection. And so this one shows a modeled nocturnal cooling rate. So if we take a look at the difference in nocturnal cooling rate using model minus measurement, we see a lot of kind of warmish grids, which might imply that the herd model tends to cool slower than the measurement. And then we also want to see if the herd model can capture the urban heat advection. So first, we define the calculation of urban heat advection. So first, we have to classify the average mean wind of each time step during the simulation period into 8 sectors as shown in the left windrows map. And then for each time step, we will define a rural temperature or rural reference as the mean temperature along the inlet side of the domain. So for example, if we have the southwest flow, the rural temperature will be the mean temperature of the all grids for the far left inlet and the bottom inlet. And if there is a west flow, then the rural reference or rural temperature will be the average temperature of all the left inlet grids. So with this in mind, we will further define the delta T, which is the temperature minus rural reference. So this delta T represents the enhancement of temperature due to the processes inside the domain, which might be related to urban heat advection. And then for each specific day, we can calculate the delta T or urban heat advection for each grid for each time step, which is equal to the enhancement of this specific day minus the average enhancement of the whole simulation period. It's kind of tricky. And with this bearing in mind, we selected several typical UHA days. So the left column is the urban heat advection calculated by the measurement or observation. And the right one shows the UHA calculated in this model, in her model. And the upper panel is the southwest conditions on September 4th. So we can see from the upper right, the model captures some UHA features, especially towards the east direction. And if the wind is northeast, which is on September 6th, under northeast flow, we didn't see any urban heat advection captured by the model because of the wrongly predicted wind direction, I would say. And under low wind conditions, which is on September 13th, we can see that urban heat advection is significantly downwind or upwind of the city. And under high wind conditions, which is the bottom panel, the measurement also did not reflect any urban heat advection. But we can see there is kind of inverse urban heat advection into the urban core, which might not be accurate. And since the wind direction is also kind of wrong. So by comparing the modeled urban heat features with measurement, we can see that the Her model cools lower than the observation during the night, and there is no clear difference between rural and urban sites. And also, the Her model did not capture the observed urban heat advection patterns for all the 4 representative nights. And so for our future task, first we want to extend the analysis period to 1 year, since we have updated all our measurements from 4 months to 1 year. So with this extended day, we better expect some more obvious patterns. And our second task is to compare the Her predicted urban heat advection under different weather conditions in different seasons to see if there is any season variability in the model predicted urban heat advection. And the final one is to compare the performance of Her using 18-hour focused with 0-hour focused to see whether the model performance can be improved with this near real-time focused initiation. And yeah, with that, I want to thank Dr. Chenghao Wang and all our collaborators from NOAA Air Resources Laboratory and Texas Tech for their constructive discussions and all the data they provided. And yeah, with that, I'm gonna end my presentation and take any questions. Thank you.
So we can go over questions both here and online. If anyone has any questions. So I have one. So you talked a little bit about like the cooling rates as you're defining them. So are you defining the cooling rate as a difference between those two times? So you have 1 and 5, and so much you can see. Are you defining those just as a difference at those two times?
I use a linear regression to calculate the continuous cooling rate. For example, from 1 to 3, 4, 5, those 5 entire hours.
Okay.
Yeah.
Okay. Thank you.
But you mentioned the resonant is measured at 1.5 meters, and you're comparing that to the Earth's meters. So how was it? Is it comparable?
Oh, I forgot to mention all the comparison for those 3 variables. I used micronet with the HERT. Yeah, so I think only, yes, 22 sites. Because there is one site we are missing data from July and August, so I exclude that site.
Do you know how temperature temperature is calculated in Earth? Because I would think if you have a prognostic variable, then it will be more comparable because the diagnostic you can just, I guess, randomly generate them from doing some translations. And it's easily changeable. If you just change a parameter, it can be easily adjusted. While comparing the observation with some prognostic variable would just incur more problem within the model instead of some feats that you can change in the parameterization process.
Oh, yeah. I think I didn't get your question, but I believe I don't know her, but I think in work, if I want to compare the urban air temperature with the other like rural, I think there is a variable which is diagnostic, which is canyon temperature. Yeah, but yeah, but I think it's a little bit tricky in 2-meter air temperature or the canyon temperature comparison, because usually they are measured in different atmospheric levels. Right? So yeah, I think we can discuss later.